In this video, I'm going to introduce the variational method, which is an approximation method used in quantum mechanics. And in the next few videos after this, I'll go through some more examples than just the one that I will use in this video. And so if we want to know the energy of the wave function, then we have our Schrodinger equation right here, which is just the Hamiltonian acting on our state here, equal the energy, which is the eigenvalue acting on our state there. So then we do the inner product here with the states, and so we end up with this part here, but the energy here can be pulled out, so we end up with this right here. But we're saying that this is orthonormal, so this inner product right here is just going to be the delta function. And so when we sort of divide through by this inner product, which is what we have here, we can just say that the denominator here is equal to 1. So we just have this part right here. And so at the ground state, we have the energy obviously being equal to the energy at the ground state. And so we're saying at the ground state we end up with this right here. And so the expectation value of our Hamiltonian here, which is defined as this inner product with the Hamiltonian in it there, is equal to the sum over I of all the states with the Hamiltonian acting on them. And that just becomes the integral in the limit. But if we can't solve the time-independent Schrodinger equation, then we can use this theorem right here, which says that the energy, the expectation value for this Hamiltonian here, the energy for that is going to be less than, or equal to the expectation value of our Hamiltonian there. And so these psi's here are test functions, which, as I'll discuss here in a little bit, there are a few things we want to consider when coming up with the test function, but for now we can just keep this more general and just say that we have these test functions psi, which will either overestimate the ground state energy or it'll give the correct answer. This works because we can express our wave function as a linear combination of these wave functions times the probability amplitude here. And because our psi here is normalized, so what this here is essentially saying is that the sum of our probability amplitudes here squared is just going to be equal to 1. So the expectation value of our Hamiltonian, which is equal to this summation here, what we end up with is the summation over our energies times the probability amplitude here squared, which we said already was equal to 1, and by definition our ground state energy is less than or equal to the E sub n here, so the state n here, and so we have the expectation value of our Hamiltonian here being equal to the energy we want to calculate, which is greater than or equal to the ground state energy times this summation here, which, as we set up here, was just equal to 1. And so we have that the expectation value of our Hamiltonian is greater than or equal to the ground state energy. All right, so there's kind of a four-part method. What I was just talking about was, quite abstract and is essentially sort of a mathematical proof of that theorem. So this theorem right here. But now we'll look at this a little bit more concretely, and then I'll actually use this four-part method in an example to make it even more concrete. But essentially, the first thing we want to do is guess the trial function. And so we do want to take a few things into consideration. And so when we come up with a trial function, we want to know the symmetry of it, whether it's an even symmetry or an odd symmetry. We want to know the number of nodes. We want to know how smooth it is, and we want to know the behavior at infinity. So how it dies off as it goes to infinity. And we want to include these adjustable parameters, so alpha 1, alpha 2, and so on. And as we'll see, a lot of times we'll just have just one of these, but there can be multiple adjustable parameters for it. Then the second part, we want to calculate the energy for it, and so we have the energy here as a function of these adjustable parameters is equal to the expectation value here of our Hamiltonian. So since we said that this was normalized, then the denominator here is going to be equal to 1. And so the energy will be equal to the expectation value of our Hamiltonian. Third, we want to adjust the alphas until we have an energy that is minimized. And to do that, we take the derivative, the partial derivative here of our energy with respect to all the different alphas. So that's just taking the partial derivative here of our expectation value of the Hamiltonian. Then fourth, we will substitute our alphas back into, well, we will actually put it into the energy here, but also into the actual wave functions in order to get the energies in the wave functions. All right, so we can look at this using a 1D harmonic oscillator. We can kind of go through this four-part method here. So this is our 1D harmonic oscillator Hamiltonian here. So first we know the following, that this is going to have an even symmetry, it'll have no nodes, it will be smooth everywhere, and it vanishes at infinity. And so a good candidate wave function for that is the Gaussian wave function. But we don't know the width of it, and so that has to be our adjustable parameter alpha. And so we can use this right here, which is the Gaussian wave function. So we have our a here, and then this alpha in the exponent here is our adjustable parameter. And so we can determine A by normalization. So we just have 1 equal to A squared times the integral of our wave function here. And so we end up with this right here. So we'll have 1 equal to this A squared times the square root of pi over 2 alpha. And so when we just do some algebraic manipulations, what we end up with is this right here for our A. And so now we know what our A is. So now we can calculate the energy. And so the Hamiltonian is in terms of the kinetic and potential energy. So the expectation value of the kinetic energy from our Gaussian function will end up being this. So this h bar squared alpha over 2m. The expectation value of the potential energy for the 1D harmonic oscillator is going to be this m omega squared over 8 alpha. And so that gives us this as our energy. So the expectation value of our Hamiltonian equal to our energy, and so we're looking for the ground state energy. So I'm using A sub naught here, and that's equal to this what I have in brown right here, then this what I have in this sort of gold color right here. All right, so third, we want to adjust the parameter alpha. And so this is sort of looking at what that function as a function of alpha would be right here. And so we will actually take the derivative of it. We want to find when the derivative is equal to 0 because we want the minimum on this function right here. So we want to try and find there. So we take the derivative of our energy with respect to alpha and try to find it when it is 0. And so when we go through all that, we find that our alpha is equal to m omega over 2h bar. So from that, we will substitute that back into our energy and into our wave function here. And so when we go through the math on that, we end up with this as our energy and this as our wave function. And if you've watched my previous videos on solutions to the Schrodinger equation, you might recognize that this is the ground state harmonic oscillator. So this should actually be a 0 here because it's the ground state. In this case, we knew what the ground state was and knew that it would resemble the Gaussian function, but the Gaussian is often used even when it doesn't necessarily resemble the ground state. The variational method is most often used to find the ground state because it can start getting kind of complicated when you look for the excited states. But we can look at what this might look like for an excited state. We'll look at the looking at the first excited state. And so now we know the following, that our symmetry has to be odd, that the number of nodes has to be 1, that has to be smooth everywhere, vanishes at infinity, but now we also know that it has to be orthogonal to the ground state because remember, our wave function is a linear combination of all of these states, and so they have to be orthogonal to each other. And so that means the inner product of the ground state with our first excited state has to be 0. So we can use a Gaussian wave function for this too, and in this case we'll use this. So we just have this B here instead of A. We still have our alpha up here, and we also have this X right here, which is what makes this orthogonal to our previous one. If having this X here makes this function orthogonal to our ground state function. So after we do the normalization, we get that B is equal to this 32 alpha cube over pi. That's all to the 4th root. So the second, we calculate the energy, and so when we go through that, we end up with this right here as our energy. So then we want to minimize the energy with respect to alpha, so we take the derivative of the energy of the first excited state with respect to alpha, and what we end up with is alpha equal this m omega over 2 h bar. So then we substitute this alpha back into our energy right here and our wave function, and we end up with this right here. So this is our first excited state energy, and this is our wave function right here. And you could keep going with this for higher energy states as well, but that is where I'm going to end this video. So I guess the take-home message for this, aside from this 4-part method, which is what we'll be kind of looking at in with other examples in the next couple of videos here, is just this idea that that our ground state energy, or whatever energy we're looking for, is going to be less than or equal to the energy associated with this Hamiltonian here. So the expectation value of that Hamiltonian will be greater than or equal to our energy. And so the energy gives sort of an upper bound on the actual energy that we are looking for. But anyway, I hope you found this video helpful, and I will see you in the next one.